in the previous lectures actually, we spoke about the concept of energy bands coming from a chemist's approach, starting with the molecular orbital theories, and of course the study of electrons in solids was much before the molecular orbital theory was invented, and it started almost as soon as the electron was discovered. Electron was discovered in 1895, and then somewhere in the early part of the 20th century, Drude came up with his theory of the electrical conductivity and other properties in metals. So what he said was the following, that is, he said Drude's hypothesis one, electrons are free to move around, or free and do not interact with each other. Two, they have mass and charge. And three, they undergo collisions basically with average time between collisions, which is tau, which we denote as tau. So essentially it was very much like the ideal gas assumption, except that the particles here have a charge. Now given this, he went about trying to explore what happens to electrical conductivity of such a material. So what he did was the following. He said basically that since mean collision time is tau, an electric field on an average acts on an electron for a time tau. So what it means is that supposing I apply an electric field E, okay. So if I have an electric field E, this acts on an electron for time tau, and then the electron undergoes a collision, and because it undergoes a collision it loses memory of everything that happened, so it has to start its journey all over again. So basically electric field is effective only for a period of time tau. So supposing this is the case, then average momentum of an electron changes by the quantity changes by delta p equal to minus E tau. Actually this gives rise to an average velocity. So on an average, this is the one. So we call the average velocity, we can now talk about the average velocity imparted to an electron is V average equal to minus E e tau by m, where m is the mass of the electron. So, you notice one thing, that is the average velocity of the electron is 0, in the sense that because there is no conductivity or no current that is flowing through the system, not conductivity but no current flowing through the system, the average velocity has to be 0. So, when you apply an electric field, it gains a non-zero average velocity, and we call this average velocity, this non-zero average velocity, as the drift velocity, and the drift velocity is actually given by drift velocity is the velocity acquired by an electron for a unit electric field which we say that the unit electric field E, which is equal to 1 volt per centimeter. So, this drift velocity, which I call equal to the V average that I wrote, is actually centimeter squared per volt second is the unit. That means the velocity that is acquired by the electron in a field of 1 volt per centimeter. Now, having said this, now let us see what we can say about the current. The current is given by what? The flux of the current is given by J equal to minus N E V average, where N is the density of electrons, where N is the number of electrons, and E is the electric charge, is the charge on the electron. Now, given this, what we can now do is we can say that the current J is equal to minus N E, and V average is given by E tau by m. You see that here it is minus E tau by m is the average this thing velocity that is you have. So, E tau by m, of course there is a minus sign there. So, I get the current density J is equal to N E squared tau by m times E. So, we know that according to Ohm's law, J is equal to sigma times E, where sigma is the conductivity. So, what it implies is that I have an expression now for the conductivity sigma, which is N E squared tau divided by m. M is mass of the electron. So, let me make it clear. Now, one can measure what the relaxation times or mean collision times tau are from conductivity measurements. So, or resistivity measurements or conductivity measurements, whatever we say. So, from resistivity or conductivity measurements, we can obtain an expression, an estimate rather, of tau, and tau happens to be of the order of about 10 to the minus 14 to 10 to the minus 15 seconds. Of course, tau will depend upon the temperature at which you are going to measure, and in fact the resistivity of a metal at high temperatures, rho of metals at high temperatures is proportional to the temperature T. So, the resistivity increases with temperature as linearly in T, and this is true only for high temperatures. At low temperatures the behavior is rather different. We will come to that some other time, but the fact that rho is proportional to T, it can also be obtained from the density of phonons that are present in the system, which participate in the electron phonon scattering. Okay, so now from the velocity which is the drift velocity acquired by the electrons, we can estimate the mean free path of electrons. So, the mean free path L is equal to V times tau, and is usually of the order of about 10 to the is roughly about 10 angstroms. So, if you assume from V is estimated from kinetic theory, let us say V is estimated from the kinetic theory. Now, it is interesting that the mean free path is in a way somewhat is like a few lattice constants. So, basically what we are saying is that mean free path is a few lattice constants, and in fact tau increases as the temperature is lowered, because the mean time between collisions reduces, and at very low temperatures you can have hundreds of angstroms mean free path. And in fact it is known that in some materials, in some metals, at very low temperatures you can have a mean free path which is the size of the sample, which is almost like a few micrometers. So, we can have tau increases as T decreases, and we can have mean free paths which are very large. In fact, one of the problems with the kinetic theory, classical theory, which is what Drude is applying, is that it underestimates the velocity of the electrons. Okay, we will come to that when we go to Drude-Sommerfeld model, and we will see a good reason why the velocity of electrons, which are actually conducting charge, is going to be rather about 100 times larger than what the kinetic theory of gases usually says it is. So, now we have been able to obtain an expression for the conductivity of a metal in terms of the mass of the electron, in terms of charge of the electron, the number of electrons which are participating in the conductivity, and the mean time between collisions. Now, we go to another aspect of the free electron theory or the classical theory, which is actually thermal conductivity. What one notices is that metals have high thermal conductivity. and insulators have low thermal conductivity. This is in general true. Of course, there are exceptions. For example, if you look at diamond, diamond is an insulator, but is an excellent thermal conductor. In fact, it is a much better thermal conductor than even copper, okay, and there is a good reason for that one. We will not go into it, but nonetheless it is important to note that metals in general have a very high thermal conductivity, and if the metals have a high thermal conductivity, is it possible for us to estimate how the thermal conductivity of a metal, how get an expression for that from the classical theory that Drude has proposed. Well, first of all, let us define what is thermal conductivity. So, to define thermal conductivity, let us take a thin wire of length L. One end of the thin wire has a temperature T1 and the other end has a temperature T2, and T1 is greater than T2. That is, T1 is the hotter end and T2 is the colder end. Okay. In this, the thermal conductivity is given by the flux of the energy that is being transported, or the heat flux, which is proportional to the temperature gradient that we have. So, this is the way we actually define thermal conductivity. Kappa is coefficient of thermal conductivity. Now, the point is that is it possible to get an expression for kappa? To get that, what we will say is that the temperature gradient is not too large, so that we can assume temperature is a constant at a position x in the interval, let me say, in the interval x minus v tau less than or equal to x less than or equal to x plus v tau. Okay, is that the right way of writing it? Okay, rather it is a constant over the following distance. Okay. Having said that, it means that when an electron undergoes a collision, then the temperature is going to be a constant until it undergoes the next collision. Okay. So, if the electron has undergone a collision at some position x, then it is going to, the temperature is going to be constant from x minus v tau to x plus v tau. So, that is what we mean by the temperature gradient is not too large. So, temperature does not vary very much over the mean free path is another way of putting the same thing. Now, having said this, now let us see, go back to the figure and let us look at any position x, and we have here we have x plus v tau, and here we have x minus v tau. Okay. So, supposing I take x to be the midpoint, okay, it is much better to take x to be the midpoint because well, let us first assume that any arbitrary x. Okay. So, what happens is that the JQ, the thermal current, can be written in the following fashion. JQ here is half the electrons are moving to the right and half the electrons are moving to the left. So, the electrons on the hotter side will take energy from the hotter side to the colder side, and the electrons which are moving from the colder side will take energy from the colder side to the hotter side. So, the half the electrons which are moving in one direction and other half of the electrons are moving in another direction. So, what is the total energy change? So, if you want to see the flux, flux is nothing but the number of electrons that are actually moving times the velocity with which these electrons are moving times the energy at the positions x minus v tau and x plus v tau. So, I can write down this one as E of the temperature at the position x minus v tau minus the energy at the temperature x plus v tau. This is the expression for that. Now, what we can do is we can actually do a Taylor series expansion, in which case we will get J of q is equal to 1/2 NVx times E at T of x minus v tau dt by dx minus E at T of x plus v tau dt by dx, and that actually gives me half of NVx. I can make, these are all x components that I am dealing with, so I can put a x here and here as well. Okay. So, again I make another Taylor series expansion, in which case I will get E of T of x minus Vx tau dt by dx into dE by dt minus E of T of x minus V of x tau dt by dx into dE by dt. Well, these things will cancel, so I can show this cancels with this one, and what I get is the following: half NVx into minus 2 Vx tau dE by dt into dt by dx. Or I can write it as n minus of n Vx squared tau dE by dt times dt by dx. So, what I get is an expression for thermal conductivity in one dimension. So, I will get kappa as equal to n Vx squared tau dE by dt. In a 3-dimensional case, what will happen is Vx squared will be replaced by V squared, and what we have is the following. That is, in 3 dimensions, what we will get would be 1/3 n V squared tau dE by dt, kappa in 3 dimension. This is because Vx squared is equal to Vy squared equal to Vz squared equal to 1/3 V squared. or rather I am not talking about 3 dimension, but I am just talking about the velocity, which is mean square velocity. If I take, instead of taking it in only along the x axis, I will take it along the in a general direction, in which case I get the expression Vx squared will be actually 1/3 of V squared. Let me make it correct. 1/3 of V squared, and so that I call it as a 3-dimensional result. So now I have kappa equal to 1/3 NV squared tau dE by dt. And what is dE by dt? So dE by dt is nothing but the specific heat, right? dE by dt is a specific heat, and we know that the energy of an ideal gas is of electrons is given by energy is equal to 3/2 n kBT, where kB is the Boltzmann constant and n is the number of electrons. Therefore, dE by dt equal to specific heat is equal to 3/2 n kB. So what I have is, I can write down for my expression kappa is equal to NV squared tau by 2 into n kB. Okay, now let us see what we can do. We can write down this expression slightly differently, in the sense that I can write down k is equal to n E squared tau by m into m by E squared into 1/2 V squared into n kB. Okay, so what I have basically done is to multiply and divide by E squared by m in order to get a comparison between kappa and the electrical conductivity. So we know that Ne squared by tau, Ne squared tau by m rather, is equal to the electrical conductivity. So I have kappa is equal to sigma electronic times m by E squared times half V squared times n kB, or this is equal to sigma electronic by E squared into n kB into 1/2 mv squared. So 1/2 mv squared is nothing but the kinetic energy of the electron gas. So from the gas laws, because we are applying the ideal gas equations for the electron gas, we have 1/2 mv squared is equal to 3/2 kB into temperature. So I get kappa is equal to sigma electronic by E squared into n kB into 3/2 kBT, or kappa divided by sigma electronic into temperature is equal to n 3n by 2 into kB squared by E squared. So you see that the ratio of the thermal conductivity to the temperature times electrical conductivity is a natural constant. Okay, it only depends upon kB, which is a Boltzmann constant, E the charge of the electron, and n the number density, the number of electrons in the system. So what we should get is that kappa upon if n is equal to 1, then kappa upon sigma electronic times T is equal to 3 by 2 kb squared by E squared, and this quantity is actually should be equal to 1.24 into 10 to the minus 13 ergs per ESU Kelvin squared. This is very close to the experimental value. Okay. So, this quantity kappa, this is kappa upon sigma electronic times T is called the Lorentz number, and that kappa is proportional to sigma electronic times temperature is what is called the Wiedemann-Franz's law. I think it is Wiedemann-Franz's law. And I think what I will do is I will stop at this for now, and in the next lecture I will continue with the discussion of the Wiedemann-Franz's law or the Lorentz number, and I will tell you what the drawbacks are. Okay? Thank you.